The first topic that we're going to look at regarding electricity and magnetism is known as electrostatics, which is the physics of charges and distributions of charges that aren't typically moving, as opposed to electrical currents and things that you'd see in wires and circuits. Where we first had experience with charges was when we rubbed two materials together, we would often see that things were attracted or repelled. So for instance, if you have a plastic ruler and you rub some fur on it and suspend it from a string, and then take another plastic ruler that you rub some fur on, those two things will repel each other. And if you take two glass rods and do the same thing, they will also repel each other. So you might think that the same thing is happening. But it gets a little more interesting where if you take one of the rulers and put it near one of the glass rods, now instead of repelling, they attracted. So when scientists first started looking at situations like this, they realized that there were two different types of charge, and they called one positive and one negative, completely arbitrary. There's no fundamental reason for what's positive and what's negative. And they didn't know anything about protons or electrons or what was giving rise to these charges. They just knew that you could create charge by rubbing different types of materials together. And this led to the rule that opposites attract, so here they attract, and like charges repel each other, which we still know to be true. Now today we know a little bit more what is going on with those charges. We know that the inside atoms, the positive charge resides in the nucleus, the negative charge resides with the electrons, which are going around the nucleus. And what is really happening is we are adding or subtracting electrons. We're typically not adding or subtracting protons. And so if you end up with a positively charged object, that just means you lost some electrons, and a negatively charged object means that you gained some electrons. And we have a law of conservation of electric charge, and this is a law that actually holds in every situation that we know of, as opposed to maybe conservation of mass. It doesn't always hold because of E equals mc squared. We never see a case where electric charge is not conserved, even on the subatomic scale, even with quarks and leptons and things like that. So let's look at what's going on a bit with this positive and negative charge stuff with this fun little applet here. If we take a balloon and we rub it on a sweater, it's going to be charged up, and what's actually happening here is we are taking the electrons from the sweater and adding it to the balloon. Now these are going to be oppositely charged, so they will attract strongly to each other. You could rub the balloon on your head if you like, and that's why your hair kind of sticks up after you rub it, because it's charged and repels each other. But you could also stick the balloon to the wall, and what that does is the negative charges here push the negative charges away. Again, the electrons are more free to move, whereas the protons are kind of locked into a structure depending on the material you've got. That structure can be different, but anyway, because these positive charges are closer than the negative charges, this attraction is stronger than the repulsion from the negative, because the distance between the charges matter, and we'll look at that more closely in just a minute. This also explains why when you walk on carpet, this works better without shoes, if you just have socks on, then you can get shocked when you touch metal. You are taking electrons from the carpet, and those electrons like to jump somewhere. Alright, so those are the basics of charge. Now we also need to talk about the difference between conductors and insulators. So if we have a charged sphere here, and let's assume these are like metal spheres, so they're conductors, and then if we put some other metal to connect the two, then we will charge both spheres. What's actually happening, since this is positive charge, it means it's lost some electrons, and then some electrons flow from this guy to that guy, so it's less positive, and this becomes more positive because it was neutral. Now if you put a piece of wood between these two metal spheres, then nothing will happen, because this is known as an insulator, and this metal is a conductor. Alright, you also have semiconductors, which are incredibly important for, that's not a C, conductor. They're important for electronics and computers and whatnot. We're not going to get into the details of semiconductors at this point, but they basically can conduct a little bit, and depending on how we manipulate them, we can make them conduct more or less and turn them on and off and those have important properties for controlling electrical devices. So how did we get one of those spheres charged to begin with? Well, you can rub it with fur or something like that, but there are some other ways. You can touch it to another charged object, and when you do that, just like we saw with connecting them with the nail, you're transferring electrons, and so you can charge it by conduction. But there is another way, what we call an induced charge. So induced. I'm having problems in induced charge. And for an induced charge, you don't even need to touch the two objects. So say you have a metal rod that's neutral, as most metal rods are, and you bring a charged rod near it. Well, this positive charge here is going to attract the electrons. You're going to get electrons flowing from this end of the rod that way, which you'll have a depletion over here, so you'll leave that positively charged, and you'll have an excess of electrons over here, so that will become negatively charged. Now, if we don't do anything else to this rod, when we remove this initial charged rod, the electrons will flow back and stabilize, and we'll end up with a neutral rod again. But we can be a little more creative. If we have this neutral rod connected to a wire, this is a symbol for ground, which just means it's connected to the earth, which we consider an infinite source or sink of electrons. It can absorb or supply electrons. Well, then when we bring, now we've got a negatively charged rod for some reason. Anyway, that's going to repel the electrons, and they'll go down the wire to ground. They'll essentially go to the earth. If we then disconnect the wire, we cut it with some scissors here. Those aren't scissors, but anyway, while this is still in the vicinity of the rod, and then we can remove the charged rod, and these electrons can't come back because we've cut off the connection. Then we can have a charged object. So this is called an induced charge, and we will see that quite often. One other thing to talk about, the previous example, we had a conducting material. If we have a non-conductor, aka insulator, then you can get the molecules can kind of realign themselves, particularly if you have polar molecules, such that you have the negative charge on one side and the positive charge on the other. So you can get kind of a small induced charge here, but it's not going to be nearly as strong as the case with a conductor. But this is somewhat what's happening when you get a balloon to stick to a wall, because a lot of times those are insulating materials and the electrons aren't going to be able to just flow away, but you'll get the molecules aligning like this to some extent, which will be enough charge separation such that you can get the balloon to stick. Here's a device known as an electroscope. Really, they just kind of have historical importance, but this does come up on the AP test, so I wanted you to see what they are. And this was one of the initial ways to measure charge. Now, it wasn't you couldn't get a good quantitative measure of charge, but you could get a qualitative measure of charge, and you could get a measure of whether charge was positive or negative. So if you rub some material that leaves a negative charge on the rod, and then you touch it to this metal ball here, that's going to charge up this ball, and then this is a metal rod here, and then you have some gold leaves, and this could work with aluminum or some thin foil that is going to be easily moved by a small force. Well, then if you bring another negatively charged object, that's going to repel the electrons, so you're going to get more negative charge in the leaves here, and you will increase the separation. So if you know it's negatively charged and you bring an object of unknown charge sign, whether it's positive or negative, and you see the leaves separate, then you know that this was also negatively charged, and vice versa. If you bring a positively charged object, that's going to attract the electrons up, and so you'll see these leaves get closer together. So whether they go in or out depends on positive or negative, and the amount by which they separate gives you an idea of the amount of charge of your object. All right, so moving on to more quantitative ideas. We know that the force between two charged objects depends on the amount of charge, and Q is the symbol we use for charge. Why, I don't know. C was taken for speed of light and whatnot. But it also depends on how close the objects are, and it turns out that it depends on the inverse square of the distance. So this is another inverse square law. We saw one with gravity, and it's proportional to the charge of both objects, just like gravity is proportional to the mass of both objects. So we're going to get a law very similar to universal gravitation, and it is called Coulombs Law. French scientist Charles Coulomb was one of the first to figure all of this out. And so our equation is the electric force, call it FEL if you will, is proportional to the charge on each of the two objects, inversely proportional to the square of the distance. And then we have a constant of proportionality here that has a variety of names, as you can read, and this is the value. A lot of times it's easiest just to use 9, and then you can assume you've got 2 sig figs, because it actually works out to be 9.0. Coulomb didn't have a way of measuring charge accurately, but what he did is, if you take a charged conducting sphere and you touch it to another charged conducting sphere, let's say like this, that was the initial situation, and then if you have two spheres and you touch them, then the charge will spread out between the two. And then if you take one of these spheres again and touch it to yet another sphere, then the charge will spread out evenly. So you know that between here and here, you've got twice the charge. And so he was able to figure out the proportions and how that affected the forces in all of this. And later on, we were able to figure out the constant of proportionality. Now, sometimes Coulomb's law is written with a different conversion factor, essentially, is what this K is. 1 over 4 pi epsilon naught. And this epsilon naught thing has an even cooler name. It's called the permittivity of free space. And in other equations involving electrostatics, they're more simple when you write them with epsilon naught. So we will kind of go back and forth depending on the situation. Epsilon naught works out to be this value here. One other thing, when we're talking about the force, which force are we talking about? The force on which object? Well, just like with universal gravitation, which I was going to write, that was gmm over r squared. So very, very similar. We have an inverse square, proportional to mass versus proportional to charge, and then we have a constant proportionality. Well, just like with universal gravitation, both objects felt the exact same gravitational force. Both objects feel this electric force. So if I have object 1 here and object 2, and they're both positively charged, they will both feel the exact same repulsive force. Same with negatively charged, and if they're opposite charges, they will feel the exact same attractive force. So as far as the signs and directions, you can come up with your own bookkeeping system if you like, but I think it's easier just to calculate the magnitude of the force using Coulomb's law, and then just kind of by inspection say, well, are they like charges or are they opposite, and so which way will they be going? Because if you have, opposite charges here, and you're going to plug in a negative value for this one and a positive value for this one, well, that's going to give you a negative force. Well, does that apply to this guy going left or that guy going right? Anyway, it just kind of gets confusing to try to keep track of positives and negatives and whether that indicates left or right or up or down or whatnot. So as I mentioned earlier, just find the magnitude using Coulomb's law, and then by inspection, be sure to remember which way the forces are going. All right, now if we have more than one charge, that's the next slide, sorry. We have what's called the elementary charge, which is considered the quantum of charge, or the smallest amount of charge. This is the charge on the electron, so we give it E. Technically the electron has a negative charge, but we could also consider this the charge on the proton. And even though quarks have fractions, you could have 1/3 E or 2/3 E on quarks. Quarks are never found by themselves. They're always bound with some other buddies, adding up to some whole number ratio of the elementary charge. So we're good as far as any physical application by saying that this is the smallest amount of charge you could ever isolate. A Coulomb of charge, by the way, I didn't mention that, named after Charles Coulomb, is a massive amount of charge. It's abbreviated with a capital C, and it is a whole lot of electrons. Typically, if you're like rubbing a balloon on your head, you're going to get something on the realm of approximately 1 microcoulomb, which is, and we're going to use this micro symbol quite a bit, comes up often because those are typical charges. That's 1 times 10 to the negative 6th coulombs, so 1/1,000,000th of a coulomb. Alright, now moving on to, if we have more than one pair of charges, how do we keep track of all the forces? Well, just like we did with gravity, you calculate the forces between all of the pairs of objects, and then you just sum those accordingly, vector sums. You might subtract them, you might add them, depending on their directions. So I'm not going to work out the numbers for this one, but if we want to find the net force acting on Q3 here, on this charged particle, well, we would look at the charge, at the force between particle 3 and particle 1, and since those are opposite, sorry, they're both negative, so they're like charges, they would repel. That's going to give us a force to the right. And then if we want to know the force between charge 2 and 3, that's going to give us a force to the left, and it's going to be a little bit larger because even though this is a bigger charge, it's more than twice the distance away, and you could do the numbers and whatnot. Anyway, you would get these two forces, and then you could just subtract those forces to get the net force acting on Q3. Also, this notation here with the 3 and the 2, that's saying that the force on charge 3 due to charge 2. I don't know why that thing keeps popping up. Alright, now let's work one example real quick. In 2 dimensions, we have 3 charges, but they're not all nicely lined up in a line. So if we wanted to find the net force acting on charge 3 over here, due to these other 2 charges, well, qualitatively, these guys are like charges, so you're going to get a force upward from charge 2 acting on charge 3. These guys are opposite charges. This guy's negative here. So you're going to get a force pulling it down this way. So your net force is going to be, something like in this direction here if you add that and that. And in order to do that, you would want to split this force at an angle into its vector components, and we will work through all that. So let's find the force on charge 3 due to charge 2, which is KQQ. Sometimes we use capital Q's, sometimes we use lowercase. Later on we'll use lowercase q for a single particle and capital Q for like a charged object or the total charge, but at this point it doesn't matter too much. That's an awful R. Okay, R squared. So I'm just going to use 9 times 10 to the 9th here for K. I've got one charge is 65 microcoulombs, so that's 6.5 times 10 to the negative 5th coulombs. You do need to write it that way because of the units with K here. Alright, then we've got 5 times 10 to the negative 5th for this, and our separation distance is 30 centimeters, so that's 0.3 meters. And make sure to square that. So this works out to be 325 newtons, and that is this right here is 325. Okay, if we want to find the force on 3 from particle 1, then we're going to have 9 times 10 to the 9th times 6.5 times 10 to the negative 5th times 8.6 times 10 to the negative 5th. And then we divide that guy by the distance of 60 centimeters, so 0.6 squared, and this works out to be approximately 139.75. So that is this total force here, 139.75. Now if I want to find this net force here, I'm going to break these guys up into components and then add those components together. So if I want the x component of this force here, then I've just got that total force times cosine of 30. So 139.75 times cosine 30, which is 121.027 newtons. Why I threw newtons in there, I don't know, but anyway, the y component is going to be same thing, sine 30, which gives you, I'm going to go ahead and call it negative at this point to remind myself that it's pointing downward, this component. Okay, so to find the total y component, I'm going to have, so this is the sum of the forces in the y direction. I'm going to have this guy, the 325, minus 69.875. Sum of the forces in the x direction, there is only one force in the x direction, which is this 121.027. go back and actually perform this subtraction, and we get 255.125. So essentially we've got 255 up, 121 over, and we want to find the sum of those two forces. So we can just use Pythagorean theorem. So the net force, and my symbols are ugly today, is going to be the square root of 121.027 squared plus 255.125 squared, and that is going to give us a big happy 282 newtons of force. If we wanted to find the angle, we could do that. Inverse tangent of 255 over 121 works out to be about 65 degrees from the horizontal right here. 65 degrees. All right, one more little step we're going to add to this problem. So we just found the sum of these forces here, which I said was 282. And now let's say we add a fourth charge such that the net force on this guy is 0. And it's a negative 50 microcoulomb charge, and we want to know what distance we need to place it. So we're going to place it along this same line, and we're not going to really worry about our angle. We just want to find this distance along the line. So in that case, we want this same force, this 282. The unrounded number was 282.376. So we're going to set that force equal to the force due to this charge, which is 9 times 10 to the 9th times this guy here is still 65 microcoulombs, so 65 times 10 to the negative 5th. This guy is 50, so 5 times 10 to the negative 5th. And then we're going to solve this guy for r squared, do a bit of algebra, and it works out to be 0.32 meters away, and that would give you a net force of 0. All right, that's it. See you next time.